Okay, welcome back to this the course on the last session on the last session, and whatever we plan to cover has been covered over this the lectures that were being that were delivered, which were broken down into modules. So, basically 39 lectures of mostly half an hour. Now, let us first have a glimpse of what has been covered in this entire syllabus, and then we plan to again revisit some of these issues, some of these concepts, work out some problems, and then and that will be that will clear if any doubt remains. Okay. So, we actually covered the first day. We introduced the subject of stereochemistry, then under it stereoisomerism, then chirality, then symmetry properties, under stereoisomerism we have divided into, we have shown what are these enantiomerism and diastereomerism. Okay, so that was the initial few days, symmetry properties. Then we went to optical activity, dextro and levorotatory, specific rotation, optical purity, enantiomeric excess. So, these are the concepts that were cleared, and then how to calculate the optical rotation, all these things. After that, we went for this 2D projection formula. And here we have covered Fisher, Newman and Sawhorse. Okay. Then we went for the absolute and relative configuration. Absolute and relative configuration. Here we have done for absolute DL, then RS and EZ. Okay. For relative we have done trio, erythro, then like, unlike, and we have done also syn, anti. There are some other methods like pref and perf, which I decided not to cover, but if you are interested you can check that, pref and perf. Okay. So, I put a star mark. Those who want to know this, you can go through the books and then see what are these. Achha. Then also we have done the prochirality. Achha, here chirality, and at that time we introduced stereogenicity and chirotopicity. That means local local chirality. Okay. We have seen carbons which are stereogenic but not chirotopic, which have seen carbons which are non-stereogenic but chirotopic. So, all sorts of combinations are there. Then we went for pro-stereogenic center, and then we have assigned and faces. So, here we have done pro-R, pro-S, and here we have done enantiotopic and diastereotopic, faces, and then accordingly we have given the names ray, psi. Okay. Then we have we went for conformational analysis. And that is a huge topic, the conformation analysis. We first covered the cyclic compounds, then the cyclic compounds up to n equal to 6, that means cyclohexane. Then we have specifically done the detailed analysis of cyclohexane. So, in between, I think what we have done, we have also pro-stereogenic centers. Before conformation analysis, we had the chiral compounds, chirality due to nitrogen and phosphorus. So, that was done, chirality due to nitrogen and phosphorus. So, acyclic, cyclic compounds and detailed analysis of cyclohexane, and then we went for we went for the decalene also, the cis and the trans, decalene, cis and trans. What we have checked? We have checked the energy differences, and we have checked the optical activity, whether they are optically active or not. Okay. So, after the conformation analysis with respect to energy, then we went for we have seen also different types of boat systems, unusual systems, where the unexpected results happen, compounds with axial groups, compounds which exist in boat conformation, that were covered. Then we went for conformation and reactivity. Conformation and reactivity. So, we went for rates of oxidation. We have given some example, rate of oxidation of alcohols of in a cyclohexane system, and we have done a reduction, a rate of reduction of carbonyl. But when we did the rate of reduction of carbonyl, before that we have done the rate of reduction, rate of reduction in acyclic carbonyls containing alpha stereogenic center. Okay. Then we did all the Cram's rule, then Felkin, and then Siplak, Siplak, all these models were discussed. Okay. And then we have SN1, SN2 reactions, SN2 prime, then NGP, then E1 and E2. E1 we did not discuss much, but because stereochemistry is involved in E2, so we went for E2 and did worked out what is the situation in case of cyclohexane. Okay. And after going through all these, then and with these are all with respect to inversion of configuration or retention of configuration. That means, the stereochemistry of these reactions were discussed in detail. And then we have finally, we came to what are called asymmetric synthesis, stereospecific synthesis. So, first we did stereospecific synthesis, stereoselective, and finally asymmetric synthesis. There is not much difference, I told you, between this stereoselective and asymmetric synthesis. A stereoselective synthesis giving chiral compounds becomes given one of the chiral compounds out of many becomes an asymmetric synthesis. Okay. Specific is little bit different. Specific is if A gives B, A gives C, and D gives D, D gives another compound. A gives C and B gives D, and C and D are stereoisomers, then it is stereospecific. That means, the product depends on the configuration of your starting material. And I gave you a classic example of what is called cyclohexene, which cannot exist in the transform. So, nobody can prove what is the state of bromine addition there. So, addition of bromine in cyclohexene cannot be called a stereospecific reaction. However, it is a stereoselective reaction. Okay. So, asymmetric synthesis, and finally, we did some asymmetric synthesis. We said that there are many approaches. One is Chiron approach, that means you have a chirality to start with. You have auxiliary based approach, auxiliary based approach, and you have catalysis based approach. Okay. We have given some examples. Chiron is that the same thing as Cram's rule, these are predicted. Achha, we have one more Cram's rule, and then we have done the Prelog's rule also here, Prelog's rule. Okay. And then the Chiron approach, that is actually basically when you have chirality already built in. So, those are like where you apply the Cram's rule, Prelog's rule, Felkin's model. Then auxiliary, we have done the Evans auxiliary chemistry of alkylation, and finally catalysis. We have given just one modern example of Barry Sharpless, so who discovered this asymmetric epoxidation. Okay. And we ended up with the mnemonic device, and I said that it is good to end up with Sharpless epoxidation, because he is the Nobel laureate, Nobel Prize winner, not in 2002. I think last time I told you 2002, it is in 2001 when he shared the Nobel Prize with Noyori, who discovered asymmetric hydrogenation, that when hydrogen comes and saturates a double bond, you can get chirality at that point also. And there are very important compounds like L-DOPA, which is synthesized by Noyori's method. And then there was the third fellow whose name was Knowles, and he started this asymmetric hydrogenation. So, these three shared the Nobel Prize. Okay. So, you see this stereochemistry subject is so important. Ultimately, all these concepts are really applicable in biology and in medicine. Biology, any biological world is chiral. So, any system you deal with in biology is a chiral system. DNA is chiral, RNA is chiral, proteins are chiral, carbohydrates are chiral. So, whatever molecules you take, it is chiral. So, whenever there is any interaction, any recognition, so it is the stereochemistry that matters most. So, these concepts that what you will be having after attending this course will be extremely helpful. For medicine also, you know that medicines, as I said, I gave you one story, real life story of thalidomide tragedy, what happens to the babies born from mother who were taking the thalidomide in the plus minus form, in the racemic form, and ultimately the babies were born with deformity. That was called the teratogenic effect. Then people realized that drugs should be given only in one chiral form. So, that is the entire syllabus that we have covered. We promised to cover this part that was in the course outline, and we have done this over this 39 lectures. Now, this 40th lecture, what I plan to do is to just to revisit whatever concepts we have covered, and then work out some problems and see, just to clear out some doubts if you have. Okay. So, first question is that you know what is which property of a molecule makes the molecule chiral. Again, going back to the very basics, chiral molecules are those which have got non-superimposable mirror images. Okay. And to have non-superimposable mirror images, it has to lack certain elements of symmetry, which are called improper elements of symmetry. So, it should lack sigma, it should lack I, and it should lack Sn. Later on I said that Sn is equivalent to S2 is equivalent to I, and S1 is equivalent to sigma. So, that you also you know that. So, it is sufficient to say that Sn axis absent is the minimum condition for chirality. Okay. When these are absent, but here you better write, because see, you have to be careful, careful in the sense that just don't go and write only that Sn axis is absent, because there may be problems, some people may not like it. So, you start with this, that it should not have sigma I and Sn, but then since S2 is equivalent to I and S1 is equivalent to sigma. So, it is sufficient to say that Sn axis absence is the minimum criteria for optical activity. Okay. Now, and n equals to 1, 2 and then dot dot dot. The molecules which lack these elements of symmetry are called disymmetric molecules. Are called disymmetric molecules. Okay. Because they could not. So, you can again another, if you are saying it in a line, you can say disymmetry is the minimum criteria for optical activity, because disymmetry means absence of this. So, that is another way to say these things, but you cannot say asymmetry is the minimum criteria, because asymmetry contains another element of symmetry, that is I. Okay. Asymmetry means devoid of all kinds of symmetry, but that you do not want in a chiral molecule. Chirality demands only the absence of sigma I and Sn. So, the Cn axis, that has nothing to do with the chirality. So, that was very clear on the very first day or the second day. Now, let us do some problems. Now, we defined I. Remember what is I? I is the inversion point, earlier called the center of symmetry. Now, this center of symmetry, the definition was that if you join one group, one substituent in the molecule to the point, to that central point, and then extend it backwards, you will find a same group at equal distance, and this is applicable to all the groups present in the molecule. Okay. Now, the question is why it is called an inversion point, because I do not see the word inversion coming in while defining the center of symmetry. Now, you will see that the definition has some problem. When I say that it hits an identical group at identical distance in the opposite direction, there is one condition which it should also satisfy, and that is when the molecule, when these groups have chirality. So, what we have earlier said is x and x. So, we did not bother whether x is chiral or not. So, if that is the case, x is achiral, then there is no problem that this matches with this at equal distance, and this hydrogen also matches with this at equal distance, and these hydrogens will of course because you have to check all sides. Okay. So, it has got a I, but why it is called inversion point? Suppose the x has got a stereogenic center. Okay. So, if it has got a stereogenic center, so that can exist in R or S form. Suppose I write that I have a molecule, both are R form. Okay. Now, I ask you that whether it has got a center of symmetry or not. Okay. We start a problem from the very basics. We will try to move forward and see to clear your doubts. So, we will extend this class a little bit. So, if this is a scenario, now I ask whether this has got a plane of symmetry or not. Now, according to the definition that I gave you to start with, initially I did not introduce this concept, now I am introducing that if you add this and extend it backwards, you get the same group. Yes, both are same group, both are X and R, but actually what happens, you will never get this XR is not the same as this XR, because I can show you in the model that see, this is suppose XR and this is XR, and suppose it is in the R configuration. R configuration means suppose this is the group of least priority, this carbon, and these are, say, white is 1, red is 2 and green is 3. So, suppose white is 1, then green is 2 and red is 3. If this is the situation and the carbon is the 4th priority. So, this what is the configuration of this? White, green and red. So, that is I see it clockwise, I see opposite from this 4th group, this I assume that this is the 4th group. So, this becomes a clockwise direction. So, that becomes R. So, my lower thing is R. Now, what about if I make another R here? So, I have to make white, then green, then red, but it is in the opposite configuration. You see, it is in the anti-clockwise direction. So, you have to change it. Any interchange will go to the other. That is the rule. If you do any one interchange, then the molecule changes. Okay. For one asymmetric carbon atom center like this, it goes to the other enantiomer. Okay. And other enantiomer. For diastereomers, it goes to the diastereomers. Okay. But R becomes S, S becomes R if you interchange the groups. I hope this is clear. If you have only one asymmetric carbon center, if you interchange any groups, you get the enantiomer. If there is another chiral center present in the molecule, then interchange of groups will lead to diastereomers. Okay. So, now let us see whether we are following the R again. This is white, this is green is 2 and this is red. So, again it is clockwise. So, these two are same configuration. Now, let us see, now you have to be careful, because there are 3 substituents. For achiral compounds we did not bother what are the substituents, but for chirality, because these are different, now you have to match the red also with the red one. Means when you add this, when you draw this line, so this is the line center and then you draw it on this side. So, the red is not, at least it is not placed on this side. So, red, if I place it on this side, I see that yes, red is, no, not that one, sorry, red should be here. So, if red should be here, now you see I add red, place red in such a fashion that it meets a red in the opposite direction. What about the green? What about the green? The green is here. Okay. The red is matching with the red, and the green is matching with the green, and the white is matching with the white. Let us see. So, this is green, this is 1, 2, 3. So, that is a clockwise direction. So, that is R. This is white, green, red, this is anti-clockwise. So, there is a change in configuration here. So, again I just repeat it, I have to make the configuration same, both are R, and I assume that white is 1, green is 2 and red is 3. So, that was not the case actually, sorry. So, now you change it, again just double check white, green and red is clockwise, keeping this as the 4th group. and here white, green and red again clockwise. So, they have the same configuration. Now, come to the point. So, this red is matching as you add, as you draw this point, join the red to this point and extend it backwards, you get red, no problem. But what happened to the green? If you add the green to this point and then extend it backwards, you find the white. Now, you can say that I will put the green there. The moment you put the green there, the red is disturbed. The red has gone from here to there. So, red will not match now. The moment you try to match white from here to there, the other two will not match. Okay, you see the point. So, that means when these groups are in the same configuration, it does not have any center of symmetry. So, now we have to revise the definition a little bit. Center of symmetry for achiral systems is that a substituent joined to the group, extend it backwards and you get the same substituent, and that is true for all the substituents present in the system. This is for molecules without any chiral center. Now, if you have a chiral center like this on two sides, then what happens? If you have chiral centers on two sides and you have then what happens? Because there is a possibility of RR or RS combination or SS combination, and interestingly when they are RR, I just showed you that it does not have I is absent. So, which form has I? Which form has I? So, for achiral molecules, now you see if I change it. So, this was earlier, this was clockwise, this white, green, red is in a clockwise direction, white, green, red is in a clockwise direction, but you cannot if you change one, make from the clock to the anti-clock, then see the interesting point. So, this goes to here, that goes to there, and now you see you will have a center of symmetry. If you have to, you just push it in the actual way. So, red matches with red, white will go to this direction. Just see, white will go to that direction, white is on this side. Green was earlier on that side. So, when you join this line, extend it backwards, it will come to this side, green is on this side. Red is going down, here red is going up. So, when you join the up one, it will go down and the red is in the down. So, what is happening now? So, if this is R and this is S, then you have a center of symmetry. So, because R going to S is kind of an inversion of configuration. So, this is called an inversion point. So, you have to define it in two ways. For systems which are not having any stereogenic center, earlier definition stands. For systems where there are asymmetric centers, then inversion center is there when the groups opposite to, in positions opposite to each other, have different configuration. So, RS has the center of symmetry, and that is why which there is a change of configuration. So, it is called an inversion point. Okay. So, that is an interesting, very interesting situation. Okay. I can tell other important problems that also you will have to encounter, and that is regarding plane of symmetry. This is regarding center of symmetry. Now, all these problems come when there is a group which is chiral. Now, suppose if I say whether this compound is having a plane of symmetry or not. Now, apparently, if these X's are not chiral, definitely it has got a plane of symmetry through this, and also it has got a plane of symmetry going through this one, and suppose this is 1, 2, 3 and 4, C1 and C3, and containing this X and H bonds. So, you cut it and you see this is the mirror image of this part. When you cut this, so it as if this is the mirror image of this part, but that is wrong. That is something wrong. If I say this is the mirror image of this part, that is wrong, because mirror image of R, mirror image of R is S. So, this cannot be the mirror image of this. Okay. So, this is not a plane of symmetry. So, no plane of symmetry. No plane of symmetry. Okay. And so, which one has plane of symmetry? You can easily make out that the one which has got plane of symmetry is this one, XS and XR. Okay. Now, there are many ways to do these problems. I can give you, this is one way that you actually see the molecule and then divide it and see whether it is one half is the mirror image of the other half. Some people who are clever, they can immediately tell that this cannot be, this cannot have a plane of symmetry, because if it has a plane of symmetry, it becomes achiral, it is not chiral. So, they will immediately take a mirror image, and in the mirror image what happens? R becomes S, S becomes R. So, this will become XS and this will also become XS. Now, S cannot superimpose on R. So, this is the mirror image of this, non superimposable. So, it cannot have any type of symmetry. It does not have I, it does not have sigma, it does not have S also. Okay. That is another way to do the problem. Okay. Now, I can go on and continue various types of problems, I think, which will be given when you take the course, and the TAs will definitely do that. I will give you one more example, that this is a compound containing 4 Xs. These are all hydrogens, 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 hydrogens. This is in R configuration, this is in S configuration, this is in R configuration, and this is in S configuration. Okay. So, now the question is which type of symmetry element it has, or is it chiral or not. If it is chiral, then it does not have any symmetry element. Okay. I am talking about the improper symmetry element, because it has got a C2 symmetry, but C2 does not count for the chirality of the molecule. Now, to do this, what you need to arrive at a decision. So, what you need to do? See, the problem is, if you draw a mirror image, you are still not, you will not be in a comfortable position, because there are 2 R's and 2 S, and in the mirror image there will be 2 S's and 2 R. Okay. So, you have to again think over it, whether it is matching on this or not. The other way is that if you are, that is why this stereochemistry, I said the visualization is so important. I see an exchange of this x up down, and also at the same time the configuration changes. So, what I do, I give it a, so as if every 90 degree there is a change happening. So, keeping that fact, what I do, I maybe just I draw it in a different way. Keeping that fact, I suppose this is 1, this is 2, this is 3, and this is 4. So, I again rotate it, say anti-clockwise. I rotate it anti-clockwise by 90 degree, and if I do that, so this is your 4 position, and this is your 1 position, this is 2, and this is 3. So, where are the groups now? So, X R will be here, X S will be here, because that was attached to the 1, then your 2 X R will be here, and this is your 3 carbon X S is here. Put the hydrogens, okay. Put the hydrogens. Now, I have rotated, the axis was what? The axis was like this. So, it is a vertical axis, I have rotated it by 90 degree, and then if I take a mirror image along this axis. So, I take a mirror image, the molecule structural means the cyclobutane remains the same, looks like the same. Now, we have to put the groups in the proper, the X's, just look at the X's. So, this is the 3 carbon, X is down, now in the mirror image X is up, that is number 1, and number 2 is S becomes R. So, this will be R. Now, at the 4 carbon, this carbon is now this 4 carbon is now this carbon. Okay. So, that carbon what happens? It was x, x was r at the top, now x will be s at the bottom. Okay. Both changes are happening, up becomes bottom, bottom becomes up, and r becomes s becomes r. So, this is s, then this is x r, and finally, you have this carbon and here x is s. So, now you see the similarity between these two. So, x, say they are same now. So, they are same. So, that tells you that it has got a S4 axis. This has got a S4 axis. Okay. So, this is quite tricky. No? This type of problems obviously, you have to practice and you can generate your own problems, not cyclobutane, take cyclohexane, cyclopentane and put the groups, especially with the chiral groups, the system becomes very interesting. Okay. So, that has got this S4 axis. Now, there are several problems I could have gone into, but the time is short. So, I will not go to many. One compound I gave it to you, and that was the alene system. In the alene system, what we have said that these two groups occupy a plane which is orthogonal to the plane occupied by this, and if AB and CD, if A is not equal to B and C is not equal to D, it does not matter A is not equal to B, A may be equal to C, maybe A equal to C, maybe D equal to B equal to D, but this becomes, if this contains, it maintains. The major condition is that A not equal to B, C not equals to D. It does not matter whether A equals to C or B equals to D. So, then it becomes chiral. Okay. Because of this can be considered that if you push this carbon and try to bring it here and then they meet each other, compressing these pi bonds, so you get a tetrahedral. So, this is, but in a tetrahedral, you know that what happens in a tetrahedral, if A becomes B, that means if the two substituents become same, that is not chiral. But as you break this carbon, as if you are breaking it and then extended it, then that sort of plane of symmetry which was present here is gone. So, alenes become chiral. Alenes can be regarded as an extended tetrahedron, but while doing that you see that your condition becomes more friendly. That means, you do not have to have all 4 groups different, here only the 2 groups at the ends have to be different in the alene. Now, if you increase the carbon chain more, what happens? So, if you have a cumulene, then what happens? Okay. The cumulene, again the thing is that these groups are again back in the same plane, So, basically it all depends on the number of pi bonds which will take care of this, that whether the groups at the 2 ends will be orthogonal or they are in the same plane. So, if n equals to even, if the number of pi bonds n, even, then what happens? The molecule has a chiral axis, then the possibility of chiral axis, because this is the chiral axis, then orthogonality is there. Orthogonality. If n is the number of pi bonds is even, then that happens. Okay. If it is odd, then it is planar. So, no chirality, because the plane of the system becomes the plane of symmetry. Any planar system, the plane itself is a plane of symmetry for the molecule. So, if you look at this, say this is a molecule which has got which is now 3 pi bonds here. 3 pi bonds. And if you take these 3 pi bonds, that means n equals to 3, you see now the two ends have become planar. The two ends are coplanar with each other. So, this is the blue and the green, and this is the white, and you can take any other. Whatever you take, it does not make it chiral, because it is a planar molecule. The plane itself, I repeat, the plane itself is the plane of symmetry. Okay. So, that will continue to do. If you put another one, then it becomes orthogonal. If you put another one, it becomes perpendicular, it becomes planar. Okay. So, just to end, I again show the allene molecule. Allene molecule will have only one double bond, not this one. Allene molecule will have, I will just rough, it is a rough showing. So, allene molecule will be something like this. This is what is the status of the allene molecule. The pi bonds are mutually orthogonal. See, these are px, this is the sp carbon hybrid, sp hybridized. Then it has got py and pz. So, if it supplies the py, then the other one supplies the pz. So, the two p orbitals, the pi bonds are basically orthogonal to each other, and that makes the two hands orthogonal to each other. So, this is allene, because n equals to 2. Then n equal to 4, another allene chiral axis will come, n equal to 6, another chiral axis will come. And we have seen how to give the nomenclature system of the allene. Okay. These are all covered. Okay. So, I think now we will when the courses start, we will put all the questions, all the assignments, so that things will be clear to you as you go along with the course. Okay. So, I wish you a very that you have a very interesting journey ahead, and you will ultimately can have very good concept about this topic of stereochemistry. Okay. Thank you.